How's everybody doing?
Okay.
Good, thank you.
Hey, everyone.
We are enjoying the unseasonable weather in El Cerrito. It's summer weather in August.
Hmm.
El Cerrito. Is it what's normally cool there?
This is usually the foggiest and windiest time of year.
Oh, okay. That's right. You're over by the water. Yeah.
Yes, we're just opposite the Golden Gate. And so all of the wind that goes through San Francisco blows over to us. But today we have sunshine. It's a pleasant change.
Cool. Yeah, I've spent a bunch of time in El Cerrito. I think it's named after Albany Hill, probably. That
Yes, which is not in
yeah.
El Cerrito, but
Oh, where is? Oh, it's in Albany. Okay,
yes.
yeah, that's right. I visited my friend who has described herself as an Albanian because she was in Albany.
Mhm.
I know the general area.
And there is Tim, who has been working on rescuing our Slack.
Yes, and if we think enough people are here, I will start talking about that. Unless I hear somebody say no, I'm going to.
I think you should, because I think we are most of the people on this track who actually use Slack.
Okay. So I've corresponded with Adrian about this, and just to bring people up to date. Yesterday, I spun up a new Colo server, and that went and you know started getting the stuff on it that's necessary to actually run it. And I was able to do that. I've done that before more than a few times, so I know what the process is. And after I got the Colo server up, I downloaded Zulip and tried to install it. The download went without problem. The installation, the first thing that happened was it complained because the virtual server I was on has only a gigabyte of RAM. It really wants 2 gigabytes. And there's a check in the script saying you don't have enough. Well, I fixed that check, so it passed it and brought it up on my 1 gigabyte server anyway. And then there was another little hiccup, but I was able to fix that. And I got Zulip running in that environment. Now I need to qualify running. There are some things that it wants. It really wants a domain name of its own, which let me put this in the chat. And you can't do anything with this IP address. It's just there sort of for reference. You can ping it, but that's about all. You can try to log in, but unless you can guess the root password, you won't be able to. Okay, so that is a domain that I set up to give to the new Colo server, and it needed that, and it needs that name to map to the IP address of the machine that the Zulip is running on. And so after that, it came up. There's another thing that it needs. It needs an ability to send email, and it may need some other things. I'm not sure about that. The installation succeeded to the point where I could connect to the website, and it said Zulip and wanted me to log in. Of course, there are no accounts on that thing. So trying to do anything gave me this error screen with a little octopus saying something's wrong. So there's still some work that needs to be done there. That isn't surprising because the setup I did on the Colo server is not what I would call complete. It really needs to be able to send email and so forth. But the installation, except for the the hiccups that happened after it started running, the installation went fine. So that's promising. However, now let me qualify my statement. I was expecting that Zulip would be like other virtual services. I run any number of services on my own Colo server, probably half a dozen. And I don't have any problem. I don't see any load on my server or an excessive amount of memory usage. Zulip is kind of exactly the opposite of that. Zulip, it seems, wants to run completely in its own machine. And it was, had a load average of 2, which now maybe that's more than it would be otherwise because of the not having RAM. But I suspect that Zulip is CPU intensive, and that's sort of a normal course of events for the thing. So I don't know what that means. The people who sell, who lease, whatever you want to call it, virtual private servers, what they give you is a slice of a machine. And so if you're trying to use all the cycles, that means there's fewer cycles for the people, the other virtual servers who are sharing the same physical machine. And I've actually seen an indication that Linode cares about this. At some point I got a mail saying, we've noticed that you've had a high load average for the last, I don't remember what it was, 6 hours, 12 hours. And it might even be a violation of terms of service to try to use more CPU cycles in some small amount. Well, small, a fraction of a machine, could be half or 2/3 or something, but trying to use, twice a whole machine could be something they frown on because they're in business to make money. They have only so many cycles. So I don't know what this portends for the long-term consequences of running Zulip on a Colo server, on a virtual Colo server.
Presumably with actual traffic, it would only be a problem would only get worse.
It might actually stay about the same.
Or yeah, okay.
Yeah,
Wouldn't be any better though.
It's hard to imagine we would
it's
generate.
highly unlikely that it would be better. Yeah, I've got a lot of traffic, so I can afford to use fewer cycles. Yeah, that's that's not going to happen, most likely. So let's see. Of course, the only way we're going to know is if we spin up a real 2 GB Colo server and try to run Zulip on it. So we had a spare 1 GB Colo server that's sort of lying around, so we reused that to do my Zulip trial. There's another thing that is clearly a necessary element, which is Zulip needs, that is to say, the Zulip that the group will use needs its own domain. And so we need somebody to pick a domain name, register it, and then we'll go through the process of, setting that so it points to the right place. There are various places that sell domain names for, I think the low end is around $10 a year. The service, the domain name that I have, I think I pay $25 a year. And I think when I checked a few weeks ago, the domain name proofmatters.org was still available. So it could be that.
Okay.
Okay, now that I've talked probably too much, anybody have a question or comment or something?
Well, another ingredient in this process is that we want to export the old data from our existing Slack workspace.
Yes.
And so last night I got in touch with Steve Vanderhoven, who was the owner of our workspace, and he gave me the rights to do that. And so I have started the export process, but apparently it takes it quite some time to generate. So it is still doing that. I started it just a little while ago.
Okay. And once we have the data, we'll have it, right? I mean,
Yes, we should have it
generated.
as of today. Anybody who adds anything after today, it won't be exported unless I re-export it. But
Yes.
yeah,
Is the exporting running on their servers then?
I believe so.
Or, yeah, okay.
And where is it? Where is the output going?
Well, I'm not sure because it hasn't completed yet, so I haven't had a chance to do it, but I assume I can download it into a file that I can then send wherever.
So
Yeah.
it'll be one large file.
I think so, but
Remarkable. Yeah.
again, I haven't completed the process, so I don't know.
How long has it been running?
Well, we've had, I guess we started this thing up on November 16th, 2016. The export process has been running, I don't know, 15 minutes.
Oh, okay.
6 years worth of data, but not very dense data.
Not very dense at all. We stopped periods where we weren't using it, so.
But that sounds great. I mean, just having a backup like that would at least allow us, even if a couple of months go by before we manage to scramble our own server and get something else up and running, at least, we could say, all right, we have all the old stuff, and if there's something you did in the last few months, just like copy that over by hand, which is probably doable. So anyway, that's a great step.
When you did the export, was there did you get a chance to say where to start? And, so.
Yes, so I started it from, yes, you have a start date option.
Okay, so if this completes then, and we continue to use Slack, you could start it, a second export from today forward.
Yes, yes. So one thing to say is private messages are not saved. The only thing are the public channels. So that's a limitation, but I assume we haven't sent too many private messages.
Yeah.
Also, the idea is to load after this file into the new server. Do we know if it is compatible with the?
Right, Zulip is supposed to be able to import the exports from Slack.
Okay.
So theoretically, we should wind up with something that looks very much like what we have now, just at a different URL.
I just put up my direct email address, anticipating a time when Slack will be unavailable or something. So if people need to get in touch with me, they can send to that email.
send you a test message to make sure I can.
Okay.
Cool, thank you. Both of you. So,
So when I
Mhm.
connect to the zulip.linuxsc.com, it just says internal server error. I
Yes.
guess, is that big?
After I,
Yes.
after I ran the thing for a while, I, and saw that it was basically doing nothing. I turned it off. Turned out it took some effort to discover how to disable it. It's not, it doesn't fit into the standard Linux service pattern. I mean, normally services on Linux you access with a command called service or systemctl, but Zulip lives outside of that. It really wants to be the only thing. It really wants to take over the machine that you're running, as best I can tell. So after I tried it a few times and had it do nothing, I turned it off. So
Okay.
there's another thing about Zulip. Maybe I could start it again. I'm not sure if I could. I will try to start it again and see if I can do that. An interesting thing about Zulip is that even though it's being run on a standalone server, it really wants to integrate into the Zulip community. The web page that comes up looks like an ad for Zulip. I mean, you scroll down and you see all this stuff about other places that are running Zulip and, you know, something. So it's, it was not what I expected. I mean, other services I have run, they are perfectly happy to run in this, what I might call a standalone mode. And it looks like Zulip is not that way. It really wants to be part of some larger community, even though you're running it on your own server. So I don't know what the consequences of all this stuff is. It was just sort of surprising to me.
I digress for a moment. I seem to remember that we had a brief visitor, perhaps a year ago, who pointed us toward a discussion group with a similar theme. And I don't know what the platform of this discussion group was, but I looked at it and it seemed fairly active. Does that ring bells with anyone else?
Another meetup group or?
I don't think it was meetup. It was more like a messaging, you know, like a forum. Anyway, if that exists and I could track it down, that might be another option. So,
Yeah.
hi, Andrews.
Hello. Hey.
Yep, hi. We're talking about our Slack channel replacement, so
Yes.
you haven't missed anything.
I
I'll
propose.
just say hi. Hi to everybody. Thanks for letting me know.
So
There
what
is
happens on, sorry, Adrian, it's the end of the month, Slack's new policy goes into effect?
I believe it is, yes, the 1st of September.
And at that point, when we go to Slack, we would no longer see anything older than 6 months or whatever it is?
90 days is there.
Oh, okay. That's
Okay.
pretty- Yes.
Yeah, that's pretty restrictive.
Oh, there we go. 500 kbytes for all that fuss. Okay. So now I
Half a
have,
gigabyte.
Half a megabyte,
Yeah,
right.
that's
500
That's-
kbytes,
That's not
that's
very much, yeah.
undoubtedly compressed.
one photo.
Yeah, one
Mhm.
photo.
worth of data.
Thank goodness I don't have a picture.
Apparently, we haven't been putting a lot of videos or
Video.
anything. Yeah,
Right.
which is good.
Does that include also all the audios that have been recorded?
No, I don't think so. The
No, I
audios
think
go
those-
onto
Zoom.
YouTube.
I mean, YouTube. Yeah, that's right.
Oh, I see.
And that's a process that Sergey does by hand, I believe. I think he extracts them from Zoom and saves them on
Yes.
something like that. Sergey may be back. Hi, Sergey.
He connected in, but I guess he's
Mhm.
away right now. Although his mic is open.
Well, if we're done with the discussion about the server, I have a question that I wanted to ask the group. This is regarding the con extension representation of the code of Yoneda. And I wanted to, if we are willing to move on.
I think we will.
Okay. Okay, let me share my screen for once. I have a little diagram that I wanted to share. Okay. Are you able to see this diagram?
Yes.
Yes.
Good. So the problem is, the issue I have is, I don't know if you can see my mouse moving, but
Yes.
okay, good. So this is the oh, I should have added I think this is an injection here.
Yeah, I think so.
Yep. Okay. So this is a injection. But anyway, this is the representation. And so you have this product, this indexed over C arrow X, and this product indexed over C X Y over the Y's. And then you have the two functions, which I'm calling F and G. And then we have this equalizer arrow. Now, what I don't understand is the description of F and G. I think I understand one of them, but I don't understand the other G, how it's defined. The definition is that F is a projection to the component indexed by C arrow X arrow Y. And then G is a projection to the component indexed by C arrow X, and then acts by F on the second map X arrow Y. Okay, so to understand this, I made it really concrete here. So
Yeah.
supposing we have a situation where we have a C arrow X1, which I name H1, and then X1 goes to Y11 and Y12 with arrows K11 and K12, and then same for X2. So the product indexed by C arrow X, I'm assuming there's only X1 and X2. So this is it, right? Cross product.
Oh, I was thinking it was indexed by the actual arrow between C and X.
Yeah, I think it is. I think you have a separate factor for each arrow coming out of C.
But then, okay, if you're indexed by each arrow, I have two arrows, H1 and H2.
Yeah.
Mhm.
So what is the X here then? Isn't that the object X1?
Yep.
So I'm,
Yep. No, I guess
right?
I think that's right. Yep. So I guess CX. Okay.
I mean,
so
if there are multiple arrows into X1, then maybe there are two. Okay, that's true too. Okay, I see. So it's possible that there's another arrow, two arrows from C to X1, in which case we would have two versions of FX1, one for H. Ah, okay. Interesting. Okay, so this is indexed by H1 and this is indexed by H2, even though we have X1. So there is possible duplication. Okay, but anyways, my
Yeah.
understanding of one of them is, let's say I belongs to FX1 and J belongs to FX2. Then I'm going to define F as K11 of I, K12 of I, and then K21 of J, and K22 of J. Because K11 maps from X1 into Y1, and K21 maps from X2 into Y2. Now, is that correct? Oh no, I'm missing an F here, right? Okay.
There's one possible problem, which is that FX1, let's see, I'm looking at 654. So the
Yep, 654.
the ambient category is arbitrary. Well, it has product of equalizers, but it's not set necessarily. So we can't confidently speak of I being an element of FX1.
Okay. Okay, I think I'm missing the functor as well here. There should be a functor F in front of all of these. Right? Because we're mapping from F of X1 into F of Y1, and the arrow K11 is going from X1 to Y11, so I need a functor applied to a K11 before I can apply it to I. But okay. But I'm puzzled how to define the next one. But maybe the fact, okay, maybe the fact that I'm indexing over the arrows and not the objects, the domain, codomain, maybe that's the key that I'm missing.
Because yeah, I was struggling with this. I think the pi is like dependent products, which is kind of like a kind of function. They're more, you know. So,
I'm just curious, is the Y fixed maybe? Maybe, you know, the X is varying, but maybe the Y is fixed. They're all going into
No.
C.
no, I don't think so.
No, Y is varying over here, right?
Well, C, so for example, C is fixed, right?
Yeah, C is fixed. C
so
is
what-
the only thing that's fixed.
Y is fixed. Okay, so then I'm wrong. Okay.
And we're looking at all arrows from C to X to Y, right? And here we have 4 of them. Let's not include H0 for now, for simplicity. And so if we think of it as set, you know, I and J gets mapped to F of K1 of I and so on, okay? So to me, that's what this projection to the component indexed by this, right? C arrow, X arrow, Y, but we're only concerned about the Y part of it. Although it's possible that there are multiple arrows between objects, in which case there would be a repetition of them. So I didn't think of that, because these are indexing over arrows and not objects. Yeah.
Right. So could it be that, you know, the first part takes you from C to X, and then you're using F to lift the X to Y arrow to get you to from F of X to F of Y.
Right, that's what I'm doing here. F is
that's the first one.
Yep, K11 and K12, right? So that's lifting this part of it. So am I doing G here instead? I'm projecting to the component indexed by C arrow X, and then I'm acting F on the second map. So maybe this is actually the function G that I'm doing.
Right.
In which case, I'm not sure what this means. The projection to the component indexed by this. Oh, wow.
Could it be that you take the composite of those two? So it would be sort of the composition of H1 and K1. Well, K1 after H1, and that you lift by.
But may I
source,
where does
the
it
source
say
is F of X?
Oh,
where
you're
does
right.
it say that Y is not fixed?
Where does it say Y is not fixed?
Yeah.
because it's appearing as a bound variable here, right?
But so C. Oh, let's see.
Right? C is fixed, but X is appearing as a
Okay,
index
okay, then that's
index
the reason.
parameter.
Okay,
Right.
you're right. It's the,
So yeah, so this
Well-
is all arrows C into X for any X. If there's an arrow from C into X, then that's what we're going to take the product over. And then this is all arrows that includes X and then Y. And then we're taking the product of all those Ys where such an arrow exists.
but how do you know it's product over Y instead of over X?
It's product over
Because
everything, like
Well,
everything
but
that's.
what about C? You see, like, I'm just saying,
C is
Yeah.
fixed. And so that
Right.
first pi is actually over two things, X and then arrows from C to X.
right. So in this particular case, in my case, there are two arrows. There's H1, right? Into so there's an H1 arrow, which is C into X1, and then there's an H2 arrow, which is C into X2. So that's why I have F of X1 and F of X2 here, right? So these are the two arrows, H1 and H2. And then these four are the four arrows that are composition of H1, K11, K12, and so on, right? Now, I did not take into account that there might be multiple arrows between C and X1, in which case there would be more than one copy of X1 here, right? For each of the arrows.
Mhm.
I didn't take that into account, but maybe,
I think there's
if I-
something else. Sorry, go ahead.
no, go ahead.
I think there's something else going on too, which is that so the first product there, the product over C into X, that's product over all arrows from C into anything. And we do have an arrow from C to Y11, right? We have the composition there.
I see.
So if we want to look at all to be thorough, and I think we do need to do, I think this is exactly how we're going to define little f. We need to throw that in, not just fx1 and fx2, but fy11 is also floating around as part of your product.
But isn't that the
Hmm.
same as the composition of these two?
Sorry, isn't what the same?
Isn't this direct arrow has to be by composition of this and this?
Yes. I mean, there might be others, but as far as we know
Right.
know that that composition exists for sure. Yes.
So
I'm
that's
looking at
taken care of.
So I think both of these pies end up being basically functions, right? So that first pie, one of the arguments for the function is X, and another argument is an arrow from C to X. And that's a function we can use when we're trying to come up with the function on the right for the second pie, which is a function that takes an X and a Y and the two arrows between them and then yields an XY. So kind of along the lines of what Hugh was saying, it's possible we can go back and plug Y in for X in that first function, and that might give us something that helps us
I think that's
implement
exactly
the
what
second
we do
function.
for little f. Yeah.
I'm looking at the definition of equalizer diagram in Wikipedia, and the way that it's described there, if I understand correctly, is that these products are really to be thought of as sets. And so F is going from the first set to the second set, and G is going from the first set to the second set. And then the whole point is that this is an equalizer diagram, the equalizer of these Fs and Gs.
Mhm.
When the elements X on the left-hand side, the elements on the left-hand side have it so that if F and G of the same thing are equal. So,
Yeah.
so that ends up being kind of like what I was saying, so if they're equal, that means that they are ending up with the same Y, right? So Y is ending up to be, and then
Yes.
also X is ending up to be the same. So,
Yes.
so as a product, it may be all disparate, but when you look at it as an equalized diagram, it's saying that F and G are going to be
That's what I'm,
equal-
right, that is what the equalizer definition is. What I'm not sure about is what is exactly F and G,
Right,
right?
right. Yeah,
Oh, I think
That's
that,
what
so F
that's
and
what
G
I'm
are, F and G, I think are by a concatenation, by post composition. So like F and G are basically, I mean, it depends on what
Hmm.
world we're talking about, but there's a world, if you look at the world of the category where C and X lives, there's going to be morphisms, there could be many morphisms from X to Y. And then if you elevate that up to these products, well, they're going to be, F and G are basically going to be concatenating some kind of X and a Y.
but
And
that's
so
not, that's
how it
not
works.
quite what the author is saying here, right? The author is saying that
yeah,
it's
it's a projection.
the upper right box there. She actually
Yeah, here.
describes what F and G are supposed to do, and the problem is to understand what she means by that, which is,
Yeah.
can I
So what
offer?
does she mean by projects to? I was kind of confused about that. One
Yeah.
of the parallel maps projects to the component indexed by the
You see, that-
composite, blah, blah, blah. So
Yeah, what
when she
one
says
definition-
component, I think natural
Okay, but those are-
transformation, right? So it seems like there's natural transformations in here, but what is projects to? Is that that's
To
just what
me-
the result is?
to me, the component is each one of these, okay? And then it's indexed by the arrow, which is what this is, right? This is the C into H1 into K11 arrow is this one, and then the next one and so on. So there are 4 arrows from C into Y's, and that's why we have 4 components, right? So that's why I have this as a result. And then it's the projection to the components using F to K on K11, right? That gives us this and this. But maybe this is actually the arrow G. I'm
Yeah,
now thinking that this
I
is
think
the
that's
actual.
not quite right. I think that's not quite right. So I think the stuff you have on the right there is fine with the F of Y11 and so on.
Uh-huh.
But
I think
you don't
what
have
it means, I think what it means.
You don't.
I don't know if it's necessarily about F and G this time. I think what she means is that to go, there's 2 things going on here. There's the post composition, which would say you go from C to X, then you go from X to Y, and that gets you C to X to Y. But then you take the functor of that. So you can do it in that order, or you can first take the functor on C to X and take the functor on X to Y and then compose through the functor. Those are the 2 different directions that you can proceed here. And I think that that's what would be, that's what has to work out.
You're saying compose, one composes before the functor and the other composes after,
Just talking about F and G, I'm just saying that, like, that's the kind
but
of
they're the
thing,
same thing.
That you have to be able to do both ways, right? I guess, like, you're going to compose in the category and then lift it with the functor, or you're going to lift it with the functor and then you have to compose afterwards. That just seems more.
They're always isomorphic, right? I mean, but that's part of the definition of a functor, that those 2 things end up doing the same thing. So it doesn't seem like much of a pullback if you've got 2 equal arrows.
Yeah, I don't understand. I just thought that was in the spirit of
Okay.
what she said.
yeah,
Well, I don't want us to
It's
spend too
something
much more
like that,
time on this
though.
one.
Young Il,
But-
can I give you my guess about what's going on?
Yes, please.
So it's true that we can visualize these as sets, which may help, but
Yeah,
It's
let's
also-
be
They are
very
sets.
concrete.
they're not actually sets, right? They're in some category where products exist. That's what we know.
Right, right.
So we're trying to define this map little f. How do you define a map into a product of things? Well, you have to define it separately for each index, right? Like it's
Right.
like, yeah. So
So that's what I have here, F and I and J, which belong to FX1 and FX2.
yeah, well, actually, you have to define it for each index on the right, right? So the components are indexed by X, Y, and the appropriate arrows out of X. So an arrow from C to X and an arrow from X to Y. Yeah.
Right, right.
For each one of those components, we have to define an arrow from the left product to that
Uh-huh.
component, right? If we do that, then
Yep.
okay. And then we've defined something. All right. So if we're given an arrow from C to X and X to Y, can we find a map from the left product to FY? F of Y. That's what we want.
Mm-hmm. Mm-hmm.
And the answer, well, what do we have on the left? The left, we have this product, and the only things we have, as far as we know, the only things that we know come out of a product are projections.
Yep.
So we know that for any arrow into some object X, sorry, for any arrow from C to X, we will have a projection onto F of X.
Mm-hmm.
Okay, but what we actually want is a map a map to F of Y. Well,
Mm-hmm.
we would have one of those if we could project on a factor that has F of Y in it. Do we have that? Yes, we do, because we started out being given C to X and X to Y, right? So that means that we have an arrow, in particular, we have an arrow from C to Y. We have the composite C to Y.
Yep.
So there's an arrow C to Y. We can go back to the left-hand product and say, oh, we have an arrow from C to Y. That means we can project. And X and Y are now confused, right? X and Y are different variables, but I'm taking Y and I'm plugging it in for X. And I'm saying, okay, the left-hand product does in fact project onto F of Y.
I see.
Take that as the arrow from C to something. Does that make sense?
Vaguely. Okay. Okay.
Because this is just from the point of view of in a general category, like what do we know about these products? And we only know a couple of things, right? We know that we have the projections, and that we know that in order to define, and that's what we have for maps out of the product. And then for maps into the product, we know that we have to define them separately on each component. And then by the universal property, we've done everything. We have that gives you.
Okay. Okay.
So I think when she says project to the component indexed by C arrow X arrow Y, see, that actually fits this fits my idea pretty well, because you are taking the composite C to X to Y. You're taking the composite arrow from C to Y, and we're projecting onto the component indexed by that.
Okay. I think my left-hand side is wrong.
Right.
I'm
so
only
that's why I was
taking
saying
one arrow.
There's not just FX1 and FX2 around here. There's also an FY11, and there's an
That's right.
FY12.
You're right. Yeah.
You
You
have
have
arrows.
Y1. Yep.
And now that we know that those are there, we can say, oh, okay, just project onto each of those.
Yep. We
that
can
gives
project onto these.
map to the left.
And then these, I don't know. What happens to these?
They're still around. I think we're not using them.
Okay.
I think you're assuming that there might even be other objects in this category, right? We don't know that. We're just sort of focused on these particular ones.
Okay. This is the key. I didn't take into account all the transitive closure from C into something. I just thought of the first level. Okay. Whereas this is taking two arrows, whereas here we're taking a single arrow, but it includes all of the targets that are already in here.
Yep.
So
And
all the Y's are included in the X's here. Okay, got it.
And it is confusing because they're different letters, right? So you have to remember what they mean.
Would have been nice if she used Z or something for the first one, or
that might have been better. Yeah.
Yeah.
Yep.
They're separate. The two products are separate expressions, so they have separate, like, free variables in them, and you can just use them however you want.
Yeah.
So just to read back what I think I hear you saying is that you could take one of the maps would take the on the right hand pie would take, you know, your F from C to X and G from X to Y, compose them, and then go back to the left hand pie and use that as the X there.
Yeah,
right. To get an F of Y in that case.
Yeah. And
And
actually,
then what's the second one? And
that's a good question.
take
So the
P of X. You
one thing is
run
here,
it-
remember our options are very limited, right? What I described as like how to construct maps involving products are really the only things you have. We don't have many options. We have projections and we have, the universal property, which allows us to construct maps
Right,
into a product.
right,
Um,
right.
But yeah, so F is the most obvious way to do it, and there's a second way which is slightly less obvious, and let's see if we can understand that one. Project to the component indexed by CX. Oh, and then right. Okay. So here's what I think that means. So we're still doing the same thing. So we're trying to define the G, and to do that is exactly the same as defining what little g should be on each of the components of the second product here. So that means we're given a component. So we're given C arrow X arrow Y. Okay. Now, instead of looking at the arrow from C to Y in the left-hand product, we look at the arrow from C to X. We can also project onto that, right? An arrow that gives us an arrow from the left-hand product to f of x. That's not what we want. What we want is an arrow to the factor f of y. But if we have an arrow to f of x, we can get to f of y because we also have an arrow. Remember what we were given at the very beginning is an arrow from c to x and an arrow from x to y.
Yes.
We've already used the arrow from C to X. We haven't used the arrow from X to Y, but we could. We could take it right now. We could hit it with F, which gives us an arrow from F of X to F of Y.
Yeah. Okay.
That means we have succeeded in defining a map from the left-hand product to the right-hand factor. That's by C to the X to the Y. Yeah, and that's
okay.
It's not easy to understand, but I think that's what she means by this. So we do the we project to the component indexed by C of X, and then we use the action by F to get over F of Y.
Okay. Yeah, I think I'm gradually getting into it, getting it.
Cool.
Okay.
And there should be a way to write that down with your example, but I am not. Let's see, what would it be? Yeah, okay. So you would project to fx1, and then you would take, and then you would you then compose that with f of k11 or f of k12 or whatever.
Right. Right.
So you could probably write that down and make it sense.
Okay. All right. Thank you. That helps tremendously.
Cool. Thank you. Yeah.
Could I show something I just wrote up?
Sure. Let me
See
stop sharing.
See if it kind of looks similar. Okay, share screen. Yeah, okay. So my interpretation of the pies are that they're kind of like, they're more like functions than products. So the first one, I guess it's way up here. Let me bring it back down. So I'm interpreting this one as being like a function that takes an X in C and an arrow from C to X and gives me an F of X. And I'm calling that alpha. And then what we're trying to create is this function down here that takes an X, Y, and C and these two arrows and produces an X, Y, an F of Y. And one way to do it is to take our alpha and apply it using the first one, takes us, C to X, and then we can lift G with F, which gives us an f of x to f of y. So then we end up with f of y. The other way to do it is to sort of compose g after, well, maybe I got this in the wrong order over here. Probably the f of g should be on this side, not positive. But so the other way to do it is to take our g after f and then
Right.
use our function, saying, okay, it's what we're going to y, and we're using it to map g over g after x. Does that make sense?
Yeah, I think that's exactly right. I think you're more from the point of view of code, like these are almost types.
Yeah.
Mhm.
But I think the idea is exactly the same. The subtle point here, what is harder for me, is to figure out what it means to equalize these two things now.
Right.
Because that sort of gets into, why are we doing this again? It's a Yoneda thing. Yeah, okay, and this gets back to their theorem 3.4.12. It's we're trying to take a limit. We're trying to use this equalizer to take a limit.
Right.
Yikes.
Turns out that you can do that you can do any limit basically as an equalizer between products. And this is just a case of that. Anyway, that goes back to section 3, which I've looked at briefly.
Okay. And so why does that give us Yoneda?
It gives us Yoneda because up above in here I can share. Context, this one? Yeah. So we've been looking at this, right? You all see this?
Yeah.
Sure. So yeah, so this here we have expressed Yoneda as an isomorphism between the image object f of c and a certain limit. But it turns out that any limit can sort of be written like this. And that means that over here, instead of a limit, you can drop in f of c.
Yeah.
So that's what's going on there. And it is kind of cool that we have managed to say something which is Yoneda-like without mentioning the category of sets at all. That may be the usefulness of this, I'm not sure. But generally in Yoneda, you start out by saying, okay, there's a functor from C to set, and you do something. But there are no sets here, as far as we know. Just categories.
Well, I think those pies are sets.
Give them that way, yes. But it's just it's a category of products. They might be it might be a lattice. They might be like soups or something. It might be ands or ors. We don't know.
Well, because I looked up, earlier in her book, and I found a definition of the pi.
Oh,
thing,
that's true.
And
yes,
and it said it's the set of sections or something like that. But the word set was there. I don't exactly understand the section part,
okay.
But
yeah. Well, that may be the definition of product in the category of sets, which is a little subtle because you have to look at like how the indexing is done exactly. But like the set of all elements of the product is actually a set of functions from the index set into the appropriate factors. So that might be what she was talking about there. But this is just a category. There are no sets here.
Okay, well, the example where I found it is where C is a discrete category and the functor F is C to set. So
yeah.
Yeah.
Yeah, so maybe you're right. Yeah.
Okay.
Anyway, it is kind of
Because
cool.
that's what she's saying, products and equalizers. And I assume that's in D, right?
Yes,
Right.
yes. Valued in a category with products and equalizers. And I don't remember this terminology exactly, but the functor F is valued in D.
Right.
Yeah.
has values in the, yeah.
I see.
It's kind of cool, really.
Yeah, it is. That's why I wanted to understand. I mean, it's like, it's one of these things where she says, oh, this is done this way and this is the other one is this way. It's like, what? I need
Yeah,
to
just
see
like-
this.
Just reading that sentence was difficult for that took
Yes, yes,
Eventually, I figured it out, I think. But
right, right.
and I got.
And so
okay.
this is,
I go ahead.
so this is Yoneda in arbitrary categories, not just
Yes.
FC to set.
Yes, although I think C is supposed to be small, which is
Yeah.
actually more restricted than Yoneda. So there's maybe a trade-off going. I don't understand the set theory problems, but
Yeah, it's like
Yeah.
it's like, yeah, locally small. I mean, something like C is locally small, then F is, then the functor is small, something like that. But yeah,
so I guess when I said there were no
I don't
sets,
know.
I was exaggerating a little bit. On the C side, that's let's see, C is small, so you can totally talk about the things in C as sets. Is that right?
At least
You,
the objects.
the hums are sets, right? Oh,
Small-
wait,
What is
No,
a
that
small-
would be locally small. This is
okay.
small is more restrictive.
Yeah,
The collection of
The
objects
objects
is a set,
form a set.
and
Yeah.
all the arrows are
The arrows-
also sets. Yeah.
also- yeah. So I think that whole thing fits into sets. But when I said there are no sets, I
Hmm.
guess what I mean is in the codomain,
Right.
because
Right.
everything's happening basically in D,
Got it.
and the stuff in D
Right.
is
These
just
are all products.
abstract category. Yeah.
Okay.
The small diagram is for the limiting process, just to say that there's
Right.
defining the limit.
Yeah, you don't
Right.
normally want to take the limit of anything that's not a small diagram. I think that's just like makes your head hurt. Or it's dangerous or something. Anyway, but basically, yes, we're finding a close analog of Yoneda, which does not necessarily involve sets,
Hmm.
which is kind of cool.
Okay.
Mhm.
Oh, bye, Antonio. He's off. All right. Well, I've been doing a lot of talking, but does that is there anything else there that people want to?
So if D was set, does this end up being something that we would recognize?
Ah. Question. Let's see.
Sorry, what was the question again?
Well, if in this thing D was the category of sets,
Yeah.
then does it look like something that we've seen before? Like the more regular Yoneda?
You mean a category of sets as objects and the arrows being functions?
Yeah,
Yes.
I think then your formulation then using the arrows as functions probably makes, as a product, as a function over a certain set, I think makes sense then.
Yeah. You could do
Right.
it more explicitly along the lines that you were doing there. I don't think it's
Right.
going to be a familiar form of Yoneda because all of this involves this wacky limit.
Right.
Mm,
Comes from thinking about it in terms of a Conn extension. So I don't
okay.
think that'll necessarily make things any easier.
And again, it comes back to the whole equalizer diagram, and it's like, what exactly do we get when we
Mhm.
equalize these two different ways of doing the same thing?
But so that, I think the equalizer diagram is playing the role of the natural isomorphism, right?
Between what?
Well, the whole point of the Yoneda lemma is you have, you're comparing f of c with natural isomorphisms.
Oh, right, okay.
And so,
Or
so now
Between
you
the
have
Hom
these domains,
functor and F.
those domains are now in set, right? And so you're having these products are over set, and basically you're building set functions or something like that, right?
Hmm. Yeah,
Mm.
yeah, actually, the first thing does kind of look like a natural transformation from the Hom set to f of x to f, I mean.
Yeah, that may be there, but I can't see it personally. I just wanted to, so this is the 3, 4, 12 that she uses a couple times there. That's what allows her to do this stuff. It's
Hmm.
she only does the diagram for the dual case, right? But she mentions that the limit of any small diagram is an equalizer of pair maps between products. Yeah. So the limit is on the other side here, and these pi's are up, these are upside down, and they're now products instead of coproduct, stuff like that. But that's where she was getting that. And the purpose of this thing here is to express the property of the co-limit. And that
Mhm.
that involves like making sure that, remember when you were doing limits and co-limits, you have to make sure that if you want a cone, you need triangles to commute.
Mhm.
And then I guess for an arrow between two cones, you need upside down triangles to commute also. But the equalizing thing is what forces, the equalizing thing is equivalent to making those triangles commute. And then taking a co-limit makes it like the universal co-cone.
So the co-equalizer picks out of the domain, I mean, the range of D and C, it's picking out of that second thing, those, it's picking out some subset of those. Is that right?
Sort of. It's actually if you have a product, then it's picking out as that's confusing. We don't have the diagrams that we need here. In the case of
Oh, this is collapsing. This is more
Yeah.
like doing equivalence.
Yep, you take co-product, and then you're going to be doing an equivalence relation on this, which I think
Okay.
basically says that anytime you have two, let's see, you have a single thing over here which gets mapped to two different things in the co-product, those things need to be identified.
Mhm.
That's what happens in a co-equalizer. I'm talking in sets, but in the language of sets, basically, but that's the intuition.
Right. Okay.
And so going back to
Wow.
our here, it's going to be a sub. So F of C is going to wind up the equalizer of these pair of maps here is going to be a subset of this product. Intuitively.
So that product is the one I was saying looks a lot like, you know, in the Yoneda lemma, you have you have your set of natural transformations between a Hom set and F. Well, that
Right.
C to X, that's your Hom set, C to X, and then F of X, so it's, what am I trying to say? So a natural transformation takes something in the domain and maps it to a function between
Mm.
between the arrow in the first thing and it. Oh well, I can't say it, but
yeah, no, it's similar. It's true. So what happens? This thing is like a Hom set, and in fact, that becomes more true later
But
on.
that's like,
I think the second one would be the like if you look at this, what the Yoneda looks like, you're having natural homomorphisms. The second one is the Hom set. The first one would be the functor, let's say f of x, and so you have this natural isomorphism between f of x and the Hom sets, and there's two ways to go there. You can go, like I was saying before, you can go by post composition, or you can go by functor. And then that's what being a natural, you know, so C to X maps over to the other side. And then you know, if you extend it by X to Y, or you can lift it up first and then do that. But so for that, natural isomorphism is about, actually natural isomorphism, what it means that you have for every, when you're going from C to D, for every thing in every object in C, you have a separate component map. So for every C arrow X, you will have a, you will have like a separate map that takes you to C arrow X to Y. I think, you know, by way of post-composition.
I think, by the way,
Later
it's not so much natural isomorphisms, but natural
Transformations.
and natural transformations in general. They're not all isomorphisms.
Okay, maybe I'm wrong then. Right. Okay. So natural transformation. You're going in that direction. Right. Okay.
Yeah.
So the natural transformation. And so, and they're related. So those natural transformations are in bijective, like there's a natural isomorphism between FC on the far left and those natural isomorphisms that
Natural
the equalizer
transformations,
represents. Sorry, natural transformations that the equalizer represents. Because the equalizer, I think, is representing natural transformations, at least in, you know, and that's how I read it, you know, but I haven't understood it yet. So
That I'm not sure about.
So in this diagram, is FC the equalizer? I was
Yes.
thinking before it was some sort of additional
The arrow.
information about injecting FC,
I think
including it into this other thing. But
Yeah,
is that
no,
for,
it's the second.
Whenever you have two parallel arrows between objects, right, you can ask whether they have an equalizer.
uh-huh,
And if there is one, you can tack it on here and call the whole thing an equalizer diagram.
Thank you
Okay.
for explaining.
It's the
Okay.
object FX, FC and the arrow, the injection.
Yes,
The
yes.
the combination is the equalizer.
Okay,
Thank you.
that's good. Thank you.
And intuitively, we think of it as being probably some sort of inclusion.
Yeah.
So that it picks out, roughly speaking, a subset. This,
yeah, it's kind of what UNATA does, huh? At least in one direction,
so that's interesting.
right?
So-
For everything in FMC, it will pick out a natural transformation between the OMZ and F, and that's sort of what it's doing on that one you're pointing to.
Yeah, it may be that if you can, I can't actually do this in my mind, but it may be that if you can see the subset of these things, which agree with these, on which these two maps agree,
Mhm.
the subset of those things ideally should be, maybe you can see those as the natural transformations that Andreas was talking about. And in that
And
case,
like this is a more general case of the Oneida lemma she was saying. So it may be that like in this more general case, instead of having a natural isomorphism between FC and then the stuff on the, you have this injection. So it's, you know, it's only going in one direction because it's more general. But if you were able to focus on the image of that injection, then you might have it isomorphic on both sides. But the right-hand side is bigger than what you need for a isomorphism because it's the left-hand side is embedded in it. So the Oneida lemma in the usual case would be more restricted, where instead of having an injection, you actually injecting into the image, so to speak. And so you can actually have a natural isomorphism between the first term and then the stuff going on the second, third terms. That's my guess, but
Mm.
yeah, well, I think if we could really understand this product here, and if we could understand which elements of it are good ones, right? Because the good ones are the ones which agree for which these arrows agree. The good elements of this product are the ones for which both arrows take them to the same place over here.
Mm.
If we could understand those good elements, then the collection of those things together is the thing that's actually isomorphic to FC. I can't do that.
Yeah, I
can imagine somebody could.
Right. So it's like that first injection is sort of one direction on Yoneda, and then maybe that second, all the equalizer part kind of then makes it go in the other direction somehow. So it makes sure that it's actually an isomorphism.
Yeah, well, the equalizer thing,
Sure.
two
I
arrows
don't
impose a condition, right? They're saying that, some of the elements in this giant product will be okay and some of them won't. The ones that are okay, are the ones for which the arrows agree. And for some reason, which again goes back to this stuff up here, that is exactly what you need to for Yoneda.
Maybe it's like, yeah, that left pi is all the X's and arrows, whatever. And so it looks like a natural transformation, but it doesn't have the commuting square property. It's just the raw data. So maybe that second part is basically saying, hey, these it's a way of saying the squares commute, except you don't have squares because you're not in set. Well, you still have.
There's still
guess.
diagrams there. Yeah, I mean
Yeah, there's still
looking at it in
squares, and that's
in 3D.
probably what the Y is doing or something.
I know that the corresponding, the sort of more general case, how do I do this? Yes, this one. This more general case, like I was saying, the forcing these two maps to be the same is basically saying that your triangles commute. Is the triangles that you need to have cocones.
Okay.
So it may be, can I get back here? Oh, look, I can.
Yeah. Wow. How'd you do that?
Thank you, Wei Ning, for pointing out that command left square bracket and command right square bracket work the same way in preview as they do in my browser.
Oh yeah,
Yeah.
I find it a nice shortcut.
Yes.
That it's helpful.
If I could make the bookmarks work, that would be fine too, but the bookmarks never do what I expect them to do for some reason. Anyway, yes, so it's command left square bracket and command right square bracket if you want to play around with it.
Yeah.
Yeah.
I tried, by the way, using highlighting in preview, and it's when I get it right, then it looks good, because then you can just bring up your highlights and it will take you exactly where you want to go. But highlighting things, I haven't quite figured out how to get it to work consistently.
Yeah, I
So
don't know
somebody
what it
knows.
is. There's something there that like I'm picking up the wrong tool or something, but
Yeah.
it constantly surprises me and goes to somewhere I don't want it to. Anyway.
Right. So anyway, we're saying maybe the sort of the left
Maybe
pi is sort of
there's
the
something
raw
going on.
data of a natural transformation like thing, and then the right thing is what is sort of like the commuting square property for.
There might be something like that. Yeah. I'm not convinced that we can read it that way, but it's plausible.
Yeah, I'm not convinced either.
Because Yoneda is not
What I
trivial.
want it to be.
Yeah. Anyway, I'm going to step away for a moment. I guess I will yield the floor then. I'll be right back.
Oh, I guess my camera went off. Okay.
Since nobody's talking, I will just say, I'm following along as best I can. And actually, it's a little better this time. It's a little better today than it has been in previous days. So I'm making some kind of progress.
Oh, good. I could talk about the codensity monad a little bit.
Sure, let's jump in.
Let's see. Okay. So the codensity monad, this is her definition here. This one. And, you know, the idea is we're using con extensions to define it. So you have G going this way, G going that way, and you're taking the right con extension and you're calling it T. So basically this guy is T. And then the question is, if you have something else that looks like a T prime, then, you know, there's going to be a natural transformation going back, you know, kind of like in this picture here. And so I wrote it up kind of like this. Okay, so the con extension has a functor from C to C, and then a mapping this way from T after G to G, or actually, yeah. And then there's a universal property. And the universal property says, if you give me some T prime and some delta, kind of like in this picture, where unfortunately this G is T prime here and these guys are G's, so the lettering is all messed up, but cut and paste. Then you get basically a natural transformation this way, such that when you take this one after G, then it's the same as the original one you had, right?
Mm-hmm.
So if you take your natural transformation after epsilon, then it's going to be equal to delta. So that's kind of what I was trying to say here. So, you know, whatever your delta is, whatever.
Mm-hmm. Mm-hmm.
And then the way she defines the monad, so a monad requires like a functor, nu, and mu. Okay, and so eta. Is that eta? Yeah.
Yep.
So eta has to take you in to your monad. So in, you know, the way we think of a monad in programming, there's like a function like pure or return or unit or something like that, and it'll take a into monad of a kind of thing. And so the way we express it in in this kind of setting is that we're taking the identity functor on C into T as a natural transformation. And the way that's defined is by using the universal property, where you say, okay, I'm going to take my T prime to be the identity functor, and I'm going to take
Well, this is where the universal property comes in. Yeah.
Right. And so the other component of the universal property is this one G that basically says that if, you know, we can take one, you know, the identity after G is just G. And so, you know, we can just use the identity natural transformation here. And so that gives us basically our eta. Does that make sense?
Yep,
Mhm.
that sounds right.
Okay. And then for mu, it's a similar kind of process. You say, okay, mu has got to take t after t back to t.
Mhm.
And so that's kind of like flatten or bind or whatever they or yeah,
Join.
not bind, join, yeah. And so we again use the universal property where we take t after t as our t prime, and then you have these two epsilon maps, and gt to g is epsilon and gt to g is epsilon. You can compose these, and then you get by using the universal property, you get your mu here.
Mm.
Okay, question? Sound like
What I wish they would do here to make this a little bit clearer is to make that so there are these two like trapezoid diagrams which are the same.
Mhm. Mhm.
And the right hand one, I would like to put those three C's. I'd like to put them all in a line. That would clearer sort of what we're doing, because that would
Yeah.
help. That makes it look
This
more like
this
the
one has
triangle
to
that we
jump
know.
from the first C to the second C, or first to third, whatever. Yeah.
Yeah, but the two T's, the composition of the two T's, I would like to see them happening in a straight line, and then it looks like
Mhm.
the triangle that we use to define the Kahn extension. That
Mm.
was easier for me. So I in my mind, I shift the diagram that way. I don't know if that will help.
I kind of view it slightly differently. She's trying to make the two diagrams on the left and right trying to look the same. That's why they have the same shape. But the
Yeah,
left one is actually a pasting of the two of the Kahn extension diagram. So it's a composition. It's not directly composing two T's at the bottom. It's actually pasting two of the Kahn extension diagrams together. Does
Yep.
it make sense to look at it that way?
yeah, no, that's also true. Yeah.
Yeah.
Well, I
But
think
at some point
also
we have to use the universal property of the Kahn extension, right?
That's
So
right.
at that
That's
point,
right.
I need to know like what the three sides of the triangle are, and that's in my mind I have to kind of collapse those two
Yeah.
T
well,
things.
I think the way to think
I
about
think
it
you're right.
is that this triangle is this triangle.
Yes.
Right. And then the T prime here, the thing that you're taking as a second candidate, is this.
Right. T
So
composed with T.
This would be the same as this.
Right.
Does that make sense to you? Where'd you go? Oh, everybody's
All
still
right,
with me.
yes.
Right.
Yeah, that sounds right. Thank you.
Okay.
And the point of the left diagram is to show that T composed with T, right, does
You
make
mean this
that,
one?
yeah, does make the triangle commute, right?
Yes, because the whole trapezoid
yeah,
commutes. Yeah,
right.
because you get it by. Oh wait, I'm sorry. No, it doesn't commute. No. These are not commutative diagrams. I keep forgetting that. They're like two cells in the right because the triangles don't commute. What you have instead is
Right.
natural
You have these
transformation
natural.
filling in
right.
the gaps.
Oh, okay. So the two triangles are distinct. Okay.
Yeah, but you can
Right.
glue them together to get an overall natural transformation from the lower part to the upper part. So G and then T
Yeah.
and then T, we do have a natural transformation up to G.
Mm-hmm.
Yeah. And that means in particular, G followed by T squared, that we have a natural transformation up to G. And now we can use the Kahn extension. Sorry, now we can use the
Well,
definition.
up to T. Isn't that what you meant? Or,
Well, I mean, yeah, we can use it to get one up to T.
oh,
Yes.
right.
But
Okay.
before that, we have to show that there's a diagram of the right form, which is G followed by some functor and a natural transformation of that all the way up to G at the top. See what I mean?
Hmm.
Say that again.
So
Yep.
in order to use that, okay, so we want the right con extension of G along itself. So
Mhm.
in order to use the universal property, so that means it's a functor from which gives us the right side of that triangle, the right bottom side of that triangle, plus a natural transformation that fills in the triangle, right?
Mhm.
Um,
You mean right,
and-
like right here or right here?
Yes. Wait. Let's see. The one that fills in. No, the one that fills in is eta. So like the right con extension consists of that T, right? The T functor, but also the epsilon that is the natural transformation filling in.
Right,
Yeah. Okay. Sorry.
right.
So, and to use the universal property of that right con extension, you need a second one. The second one
Like
of those.
here or here.
Right, exactly. So we want to know that that T squared sort of fills in another candidate for this thing.
Mhm.
And it does because we have a natural transformation from the bottom of the trapezoid to the top of the trapezoid.
Mm,
Nice.
From the bottom.
Sorry, the
You
bottom
mean
of
like,
the trapezoid, meaning G followed by T followed by T. That.
mhm. Because you mean that's the epsilon composed with epsilon?
Yeah, it is, but in a kind of funky way, right? It's not just epsilon squared. We have to
It's
do this. We have
it's
to whisker
like
them together. A
yeah,
couple
it's the vertical composition of natural transformation.
Yes.
It is vertical, right? So it's the easy
Right.
one.
Yeah, it's the easy one.
but we have to whisker with T also, right?
I don't think,
Yeah.
do we? Because they're
Yes.
both starting here. Whoops, where'd my,
No, you're
They're
right.
both-
Then-
this is working, it's not working anymore.
Yeah, the diagram on the left, the mu diagram on the left, the two triangles are separately, the epsilons are natural transformations, right? From the lower to the upper. So whereas the right side is assuming that T composed with T makes the whole thing commute. And then we have a universal property that maps T composed with T into T. What I'm not quite sure is going from the left to the right? How do we show that T composed with T also makes the,
But they don't commute. They don't commute. Remember, they're not commutative.
No, I know. But how do we know that for any other T prime, right? In this case, T composed with T is T prime. Don't we
Right.
need to show that T composed with T makes the triangle commute?
No, we do need to show that T composed with T gives us, together with T composed with T, we also have a natural transformation from T composed with T on top of G up to G. We need to have, so T composed with T is just a functor that fills in, but we also need to complete the triangle, right?
Right.
And that's
Okay.
what the left side does. The left side gives us a way to
How
specify.
does it do that though?
Good question.
Are we able to compose the two epsilons? No,
Not
it doesn't.
directly.
Yeah.
Not directly. No.
No.
But the epsilon gives us a natural transformation from T on G to G, right?
The middle G, yeah.
So we're now up to the middle G, and now let's see. So Now we want to
You're talking
extend
about which one? We're talking
Yeah,
about that
this
one
one.
first, right?
Yeah,
Right.
that one
Right.
first, and then so that means that if we extend both of those functors by t, like trivially, we now have a natural
Mhm.
transformation from g then t to g then t,
Mm,
right? And
Yep.
then, so that's the whiskering part, and then we can use epsilon again
again.
to go from g then t to g, which is at the top.
Right,
wish
Yeah.
back
Just
here.
for this, but yeah.
So I think
Okay.
it's regular vertical composition though, because these natural transformations are both starting in D. So they're going to take an
Right.
element in D and give
To
us,
C.
yeah,
Yeah.
and then give us a component from C to C. And then
Yeah.
this one will also give us a component from C to C, and we just compose those in the regular
Yeah.
way
Functor
to get a
composition. Yeah.
component from C to the outside C to the outside C.
But it's
Right.
not just the composition of two natural transformations, though. I mean, because we can't
No.
compose epsilon with itself. The types are wrong.
No, the types are correct.
Oh,
Epsilon
sorry.
goes.
You're right. No, okay. Yeah, types are correct. Well, is that true?
The functors
No.
are D into C, right?
Yes, but what epsilon does is to take it goes from a functor, it goes from G then T to G.
Right.
Right.
So
Right.
you can't just do epsilon again on that, because epsilon,
Functors are different. I see.
Yeah.
Even though the codomain
No,
and
it's the
domain are the
same.
same.
It's G, T to G.
okay, but you
Both
have to
the
put that
same.
second T in, right? You got to put the second T in, which is, I think, the whiskering part. And then you can do it.
Ah,
Okay.
Anyway, this is we're yeah.
okay.
Yeah.
Whiskers.
Because
But
I think part of the whiskering, like the way I interpret it, it would be here, right? You have your mu going from T after T to T. And then if you want to combine that with epsilon, that's when you have to push it out by G, right? Because this one, kind of the natural transformation is indexed by guys in C, and
Mhm.
this guy is indexed by guys in D. So we have to push this one out by G in order to get them both starting in D.
Yeah.
I don't, so. Anyway, yeah.
But yeah,
Yeah.
so she has defined now both eta and mu, but I don't think she ever pauses to prove that this gives us a monad.
Yeah. So exercise
Yep.
656 says basically show that it's a monad.
Yeah,
Okay.
that would be a good one to do.
So why is this being weird? Okay. So here's your monad. You know, it has the three components, a functor usually called T, and then eta to take you in, and mu to take T cross T squared to T, basically.
Flatten.
So the way I did it was
Ooh,
use the
nice.
universal property, but
All right.
it ends up, we want to show, for instance, this, but I end up showing this because there's an with an extra epsilon on the beginning. And basically, you know, you basically say, okay, we're starting sort of like here. There's like two different ways to cut this up. One, you can sort of cut it this way and then cut it this way, or you could cut it this way and then cut it this way, or maybe the order goes the other way. And then so you can use the universal properties to kind of flip. You could take this guy and flip it to look like that, right? So we've
Mm,
kind of switched that around, and then we can take this guy. Sorry, my hand is shaking or something. And flip this arrow to go the other way. And then if
Mhm.
we cut it this way, then we can first flip this so that it kind of goes that way. And then we can flip this guy to go this way. And they're all equal.
Mhm.
So that ends up implying that this equals this. But
Mm,
so it's what we want because it's,
mhm.
but it has this extra kind of like starting point on it, right? Because basically I added another T at the end of this diagram. And so there's like a little extra stuff in here. Because you're going, you're trying to show this that this is a commutative square where you start with t cubed and go down to t, and then you go either this way or this way, and it's supposed to be the same thing. So here's my t
Mhm.
cubed both places,
Mhm.
but
Mhm.
to make the universal property work, I had to leave the g on the beginning, which then has an extra epsilon. So I don't know if that's the way to do it. Figured that it would have to use the universal property, but maybe there's another way to do it. Or maybe there's a way to get rid of this epsilon.
Yeah, can't
Mhm.
we just factor out the epsilon at the end? It's common.
It's common,
That
but
would be nice.
you can't just cancel it unless you've got like an inverse that you can compose with it or something.
No, this is a good
Okay.
exercise. I don't see how to do that. That's interesting.
Yeah.
Yeah.
I think the idea of the diagrams is probably exactly right. Those
Mhm.
pictures look very convincing, but they're
Yeah.
missing some little step. What I would like to do is get to a place where, like the thing on one side satisfies the universal property that this thing on the other side has. So then it has to be equal, right? Because the universal property can only be satisfied by one thing.
Mhm.
But I'm not sure how to do that.
Yeah.
Well, maybe that's the key. It's sort of like since we're saying that there are two ways to map t cubed to t. If there are two ways to do it, and the universal property is unique, then they have to
Mhm.
be the same.
Mhm.
As long as they both satisfy the condition of the universal property. Okay, that could work.
That could work.
So then you have to show that both of them do. Yeah. Oh, okay.
Well, right. We'd
I'm
have
not-
to show that.
Can you compose? I'm not sure what happens when you compose these things, though, right? I mean, we know that mu itself has a universal. Well, let's see. What can we? I can't remember. What's the universal property of mu again?
Go
back up to.
I guess I wrote it here.
Oh, okay. So
yeah. So it's
Yeah, we don't quite get the
basically takes
notation.
t squared to t by and then it's this epsilon. It's and that's sort of the equation, unless we have to whisker this or something. But so it's not really u that has the universe. I mean mu that has the universal property, is it? Or it's really the Kahn extension. But it's mu is a consequence of the universal property. But maybe since there's two ways to come up with this, they have to be the same since.
Well, mu is the unique natural transformation from t squared into t, right?
Okay.
Given by the conic extension property. So it's the arrow, it's the natural transformation from t squared into t, the unique one that satisfies the conic extension property of t. So there is a uniqueness in that sense, but I'm not sure how that applies here. I think the algebra that you did of just taking the triplet and composing it, associating it one and then the other way, okay, is probably that's the right thing to do. Using the mu property to go from t composed with t into t in one way, right? The first two t, and then the mu on the second and the third t, and then doing it again, applying it twice. I mean, in your notation, this is what always gets me, but just a reminder that on the top left corner, T3 and then double arrow into T2, the arrow T mu, the T there means the identity natural transformation from T into T, right?
Right.
And then we're composing, and that's a
horizontal, and that's right.
Horizontal composition, I think, or something, right? Or yeah.
I think that's got to be
no,
because we're composing a functor with a natural transformation. So we have to promote the we have to promote the functor to be a natural transformation, and then
right.
We can.
So T there is the identity natural transformation from T into itself.
Yeah, which I think we could also write like 1 sub T. I think people or
yes.
ID sub T.
Yeah.
Yeah.
And so that's just regular kind of regular vertical composition. So basically you apply mu first, and then you just use T to map it afterwards or something. And this is the one that goes the other way. This is the one with the whiskering, where this is really sort of saying that this T, you're sort of saying, use that to map your index first, and then use mu after it.
Yeah.
Right.
One of those two is trickier. Yeah.
Yeah, I think this is sort of the whiskering one.
I think there's whiskering involved in both cases, though, because I think whiskering is basically what you do in order to compose a functor with a natural transformation on either side.
Well,
okay.
You have it written there, right? Just below, you have mu t is defined to go from t t t, right? So it's mu acting on the object t sub small c,
right?
Whereas t mu, is t acting on the arrow given by mu at c.
Right. So this gives you an arrow, and then you lift it using the functor T.
Right.
Right. Whereas this one, you use the functor first to map
give an
your
object,
C, and then
mu gives you the arrow.
Mu. Right.
Yeah. Wow. Okay.
So I'll have to think about that. It's like the uniqueness, I keep forgetting about the uniqueness. But that could
Mhm.
be the key that, basically, since these both end up looking like con extension candidates,
Mhm.
then there can only be one for,
Yeah, if we prove that they both work, and we know that only one works, then we know that they're the same.
right,
Something like that.
something
But
like
I'm gonna have to
that,
think about how to do that, though. It's
right.
So why is it called co-density? I understand the word density now from the previous section, the density theorem 658. It's the same intuition as rationals are dense in the reals, because every real can be represented as a limit of a sequence of rationals, right? So that I understand. And the theorem that they have is the density of home functors are dense in the set of all functors from C into set. So intuitively, I think I understand. The Y there, the embedding, produces a home functor, which is a functor from C into set. And so the limit says any functor can be the limit of a sequence of home functors given by the embedding. So that I understand.
Like right here.
Yeah.
Yeah.
But I'm not sure what co-density means in terms of the monad. Why is the monad co-dense? Is it because the arrows are reversed? That's it? Like, is there a
But
dense?
you're
Is there
asking
a
about the
dense?
co part, right?
Is there a dense monad that we need to understand, or is it only co-dense monads that are interesting?
Huh.
I don't know why the
I don't
notation
know.
comes in here.
I get, if I were to guess, maybe a density monad, could that be a left con extension of a functor along itself? Or is that the wrong, that might be applying the duality in the wrong place, though.
Yeah, those are the kind of things I wish she would describe a little bit, but anyway.
It does say down here that a functor is codense if its right con extension is
Exactly.
it's the identity. But I guess you're asking more about co versus not.
Right. I mean, what does it have to do with density at all is my question.
Oh, okay.
And specifically, why is it co-dense?
Yeah, I don't know. Well, the thing on the previous page, can we go up one? Because that's when they started doing these
Like
diagrams.
this one or the previous one?
Yeah, 659. So here we are. Oh no, sorry. I guess I mean 658. Yes, the highlighted one.
Okay.
So that is a
Mhm.
case where we are in fact trying to do a con extension along the same thing, right? We have
Yep. The Yoneda embedding.
yeah, and actually, did I understand this? Yeah.
So the Yoneda embedding takes an object into a home functor from let's say X in C. It takes it to home set from X into something or something into X. All the arrows emanating from X or the set of all the arrows going into X.
Going in. Okay.
So that's what the Yoneda embedding does. So in a sense, it is a subset of all functors from C into set, right? It's only the functors that you can make using home sets.
Yeah, it's the representative, in fact.
Right, by definition, yeah. And that is dense in the set of all functors, and that's that the proof is. The proof is saying that given any functor f, we can make that a co-limit of home functors. And that's what this Y sub arrow F does, is it picks out all the embeddings and then the pi.
This one here,
Yeah. And then the pi.
because that's a common
projects it
category,
down.
right?
Right. And then the Y then projects it back into all the functors. But
Mhm.
only the home functors are projected in, right? So Y gives you an injection from, defines a subset of all the functors which are home functors. And then we take the co-limit of it, and then we get the original back, in a sense.
Yeah, but
So-
And that's what it means for it to be
In this proof-
codense, right? That, yeah, go ahead.
but in this proof, we're only looking at F. We're only looking at representable F. We're not looking at generic F from C to set.
No, the Y down arrow F, right?
Oh,
F appears in there, yeah. So these are all arrows from the functor, the embedding functor at Y into F. And so in a sense, that's where the approximations are, right? So we're looking at all the approximations of F that are kind of representing using Yoneda embedding. And then we're projecting those down and saying all the C's. And then we're now creating the home functors all over again, back into set C to the C power.
what I don't really see here is something that says, okay, give me any functor. Actually, well, here remark 659 seems to be doing what you're talking about.
Yes.
You take any functor and then you take a con extension along. I'm a little confused now. See,
Right. Con extension along Y.
yeah, but why? I mean, when we're doing an extension, we think of, yeah, okay,
Into a larger domain.
yeah. So the domain I was thinking of was like all functors are included into representable, or sorry, representable functors are included into all functors.
Correct.
That's the extension I'm thinking of, but I don't see that here. Because set C op, that the bottom of the triangle is not like, doesn't give us all functors. That's only the, oh wait, it does.
No, it does.
I'm
It
wrong,
does.
It does. Yes, sorry.
Yeah. That's the thing. Set to the power C
right.
is
Right.
all functors.
Sorry. Yes, you're right.
Functors from C op to set.
Yeah.
Right. Whereas Y embeds, gives you
Certain functors.
right, representable functors over the index category C. Right.
Okay.
So, yeah.
Cool. Thank you. But anyway, so we were trying to figure out why they're using the word density the way they are, and what I was going to point
For
out
the
is that
monad.
658 is the place where they start using density, which something about density means like extending a functor along itself.
Right. Right.
And not totally, and in that case, you do get one, and the footnote says that means that the Yoneda embedding is codense by definition. Has whatever it is, right? Oh, it's left here. It has a con extension of some kind, and that extension is the identity, which is kind of what you would expect it to be, because it's the thing that actually makes the triangle commute.
Okay.
But it's not. So yeah, so maybe if you think of this diagram as talking about density, then you can kind of generalize that to mean a codensity monad is the other things that you can get from this diagram, other than the identity, right? Because if you have a codense functor, the thing that will be filled in for the dashed line will be the identity. That's what codense is. But you could also get other things potentially, and any of those is like density related somehow. I don't know.
Huh.
I agree. It's not all that clear. We are running low on time. I wonder if we should look in it. No.
Yeah.
Big question. Are we done? Have we
That is a question.
gone as
So,
far as we can go?
well, have we gone as far as we can go? That's probably yes. But are we done? I think that's no. Sorry to be so realistic.
I kind of want to work
Yeah.
on Peter's exercise now to
Yeah.
fill in the gaps of that thing that the codensity monad actually is a monad.
So you're
Uh-huh.
signing up to do that for next time?
That would be nice. I'm sort of curious about there's something in there about simplicial sets, which I think are kind of cool. But
Mhm.
Another exercise.
Yep.
It looks like exercise 655. Anyway, I mean, I'm curious about that. There are lots of codensity monad examples which all require, extra math that most of us don't have, and most of which I don't have. So we don't need to do all of those. But anyway, I could chew on this section a little bit more, or
Okay.
not. But I think we should also be thinking about like what's next. And there were a couple of
Mhm.
one or two nominations earlier.
Yeah.
Jesus had a paper. Maybe we should discuss it at the beginning. There are more people, but maybe we should kick it around on Slack as well.
Well,
All right.
I'm still pushing for Sergey's book,
Oh, right.
which is not category theory, but a whole new adventure.
Sorry, did you suggest we continue the question of what we're going to do next time on Slack?
Well, I think if
I think maybe we should spend one more session on some of the exercises maybe next time.
right,
I'm in favor of that.
And then
Okay.
after that, we can maybe jump into one of the papers
And-
that Sergey
And furthermore,
suggested.
let's allocate some amount of time at the end of next session to talk about where we're going next.
Or at the
Yes.
beginning.
Or at the beginning, just-
Beginning or end, but more than
Yeah.
just 2 minutes when we're out of
Yeah.
time.
Yes.
Right.
People drop off toward the end, so maybe we could start next time.
Beginning
with-
is fine, I don't care.
Okay. Sounds
I
good.
mean, just quickly, one thought I had, it's like, I keep finding myself going back in her book and finding all sorts of interesting stuff I'd never really gotten. It's almost like I want to let's start her book from the beginning.
Read the book.
Well,
I mean, because she goes right into functors and Yoneda like right away, so it's not
Yep.
like we would be,
Well, let's
starting
continue
from
that.
zero.
I think your point is good for discussion. Let's continue that in the next thing.
Okay.
Mhm.
mhm.
Okay, so that's one
And
option.
I just want to thank you. I learned so much about font extensions. And I'm just very grateful for all I learned. Thank you to everybody. And so I'll keep going, as long as we can go. I'm very happy.
Okay.
Okay,
Thank you.
So
so
same time, 2 weeks?
same time, 2 weeks. Any objections?
That's good.
All right, so see you all on the 27th.
Right.
Okay,
Yeah. Okay.
I'm
Yeah.
not sure. I may be traveling, but
Oh.
anyway, I'll try, and if I finish the exercise, maybe I'll publish a little summary or something.
Oh, no, we were
How
hoping
about-
that you would
how about the
be
week-
carrying.
How about the week after?
Okay, let me look.
Is
Um,
3 weeks workable for you? I enjoy your participation. I don't want you to be gone.
No,
Yeah.
I enjoy it too.
I will be gone the week after, but yes, no reason the meeting cannot happen without me.
Let's see. Thing is, I'm gonna be hanging out with my family for like 2 weeks, and I'm reluctant. I can't guarantee. I can't guarantee
I see.
to be in there that time. So yeah. Why don't you do? Yeah. Sorry. I will.
Well, if you're going to be with your parents for 2 weeks, why can't you take off 2 hours?
Yes, yes. I don't know. So I'll be,
Have them join the
I'll
meeting.
probably be kind of jet
I'm just
lagged.
kidding.
Yes, I can
Ah.
invite my little siblings in and so on. Yeah,
Yeah.
that might be fun.
I should say also, I expect to be distracted over the next couple of weeks trying to get a server and so forth up. So I will have correspondingly less time to devote to the study of category theory. But anyway, whatever time you guys think is okay, that's okay.
I mean, I will be back, but it might just take a couple of meetings. So until then, I'll do what I can asynchronously on Slack, and if I can fill in an exercise or something, I'll try and do that.
Slack may disappear before.
Oh, that's right.
It may.
Well, no, not that only the older things will disappear, right? Everything new that we
Right.
see.
Oh,
should
the
still-
older.
So it'll
things
be there
disappear.
for 90 days.
I see.
Were
Well,
you-
that might be viable then. Okay,
What do we end up with, the 27th or October 3rd?
You mean September?
September 3rd
Yes,
is a
yes,
little
yes,
easier
yes,
for
yes.
me. We could try September 3rd.
Okay,
Um,
I will not be here September 3rd, but you guys carry on and tell me what the next meeting will be after that, so that I can schedule it. Because
The content of the next, yeah, the time and
also the
content.
time.
I'm in content, yes.
Okay, I will try to make it.
All right. September
Mm-hmm.
3rd, okay.
Okay,
Yeah, but don't push it though. I mean,
Yeah,
okay, great. September 3rd. All right.
all right.
Thank
See
you.
later.
Bye-bye.
Okay,
all right,
See you all.
bye.
bye.